Hello, my name is Prathamesh, and let's continue with our discussion of permutations and combinations. Okay, so last session we looked at the definition, the properties, and a few examples on the factorial. Right, so the factorial of n is equal to n into n minus 1 into n minus 2, n minus 3 multiplied all the way till 1. So now let's try to understand the most important part of the chapter, that is actually permutations and combinations. So before starting this topic, or in order to start this topic, I'd like to take an example. Say I have to give away 3 pens. There are 4 ways, or the question that would naturally arise is, how many pens can I give away? If I have 3, how many pens out of 3 can I give away? So I can either give 0 pens, that is no pens, or I can give 1 or 2 or 3. So if n is the total number of ways to give away or to select r pens out of n 3 pens, first possibility is 0 pens. So this is just one possibility, that we don't give away any pen. Second is 1 pen. So there's 3 possibilities. If say the pens are of different colors, like R, B and G. Right, so these are 3 distinct objects again that we're dealing with. Remember the definition for the factorial, it involved the word distinct, and the same applies in these cases. So 1 pen can be given away in 3 ways, either red or blue or green, or 2 pens. 2 pens can be given away in the following ways. You can count for yourself: RB or BG or RG. So 3 ways again. Or 3 pens can be given away in 1 way. I just give away or select all of them. So n will be the addition of all of these number of ways, right? Because I cannot simultaneously give away 0 and 1 and 2 and 3 pens. I have to either give away 0 or 1 or 2 or 3. So n is 1 plus 3 plus 3 plus 1, 8. Now you can repeat this exercise for 4 pens. Perhaps there's another color, like R, B, G and say Y, yellow, right? So again, there's the first possibility that I give away 0 pens, 1. The second possibility that I give away 1 pen, 4 ways to do that. The third is 2 pens. Now 2 pens I can give away in the following ways. Again, you can count for yourself: RB or BG, RB or RG, RY, BG, BY, and one more, GY. So 6 ways. Another possibility is I give away 3 pens. So 3 pens I can give in RBG or BGY, RGY, or RG, RBY. Yeah. So again, 4 possibilities. And the final one is I give away all the pens. So 4 pens, one way to do it. So n is 1 plus 4 plus 6 plus 4 plus 1 equals 16. Okay, so you can repeat this exercise for 5 pens as well, but obviously that's very tedious. So instead, perhaps we can look at for 2 pens. For 2 pens, there's 3 possibilities: 0 pen, 1 pen, or 2 pens. Now, I won't write each individual possibility, you can count it for yourself. But you will find that for 2 pens, the total number of ways to give away these 2 pens is 4. Right? I either give no pen or both the pens or one of the pen, and there's 2 ways to do that. So 1 plus 2 plus 1, 4. Obviously, now you can see a pattern, right? For 2 pens, the total is n equals 4, or we can say 2 square. For 3 pens, n is 8, or 2 cube. For 4 pens, it's 16, or 2 power 4. So for 5 pens, we can speculate, or we know for a fact, because a pattern is followed, that the total number of ways in which we can give away 5 pens, or we can select 5 objects, 5 distinct objects, is 2 power 5, or 32. Now, this is well and good, but let's try to look at the um, individual number of ways of selecting r out of n. So what you can do is say the number of pens is or number of objects, the number of distinct objects is denoted by m, the number m. If we take the number m equal to 0, there's just one possibility: I can't do anything. If we take m equal to 1, either I give it or I don't give it. So I can write 2 to the power 0, 2 to the power 1, m equals to 1, 2, 1, that's 2 power 2, m equals 3, 1, 3, 3, 1, 2 power 3, sorry, m equals 4, 1, 4, 6, 4, 1, 2, so that's 2 power 4. These are the cases that we have computed. Now if you see, we can also find all the individual number of ways of sampling r out of n, where r is less than n, objects. So what I mean is, for m equal to 5, we can also find out the number of ways required to select, say, 0 out of 5, or 1 out of 5, or 2 out of 5. If we follow this triangle, this is also known as Pascal's triangle. So 1, 1 at the extremes, 1 plus 4, 5, 4 plus 6, 10, 6 plus 4, 10, 4 plus 1, 5. And this should add up to 2 power 5, 32. Now obviously we do not have the means to construct this triangle for every kind of problem, because it can be very tedious for a large number of objects. Say m equals 15 or 10, even larger than that. So we need to try and look at the pattern that is followed by the sampling or the selection. Okay, so this is where the concept of permutations and combinations comes in. If we look at permutations, in order to understand permutations, let's take the same, or let's take n objects, right? N distinct objects, and we have to select r out of them. R have to be selected. Obviously, R is less than or equal to n. R cannot exceed n, obviously. So there's R places, right? 1, 2, 3, 4, all the way up till R. Let's try to do a sort of analysis like we've done before for the before problems. Now the first place can be filled in n ways, right? The first object can be selected in n ways, because I have n objects or n distinct objects available. Now the second can be filled in n minus can be filled in n minus 1 ways. The third in n minus 2 ways, right? You can see the pattern, and the last will be filled in n minus r plus 1 ways. Note that this 1 plus 1, this is important. It won't be n minus r, it will be n minus r plus 1, right? So what we are doing here is we are simultaneously selecting the r objects out of n, and we are also arranging them, right? The arrangement matters. So what I mean by this is, say the case of 2 pens out of 3, R, B and G. If I am taking a permutation, it means that I'm making a distinction between R, B and the case B, R. These are two different permutations. They comprise of the same set of objects, but the order of arrangement is different, and that is called a permutation. If I select the object and the order in which I have selected the object also matters, then that is a permutation. So this result, number of permutations of R objects out of n. So this number is equal to n into n minus 1 into n minus 2 into n minus r plus 1. Now, but this form so the number of permutations of R objects out of n is n into n minus 1 into n minus 2 up till n minus r plus 1. But this form is a bit tedious to compute often, so we would rather express this result in terms of another simpler result, and we know how to do that, because in the last lecture, as you saw, we know how to compute factorials. So if we try to convert this formula into the form of a factorial, n into n minus 1 into n minus 2, now this number can represent the factorial of n if I multiply it by the remaining numbers, right? So after n minus r plus 1, in order to complete the factorial, I must multiply by n minus r and n minus r minus 1, n minus r minus 2, all the way up till 1, and divide by the same term. So the numerator will just become n factorial, and if you look closely, n minus r into n minus r minus 1, n minus r minus 2, this product is the factorial of n minus r, right? This is the factorial of n minus r. So this gives us a very important result. The number of ways to permute r objects out of n, or the number of permutations of r objects out of n distinct objects, is equal to n factorial by n minus r factorial. And we denote this in the form of a notation npr, number of permutations of r out of n objects, or npr, is equal to n by n minus r factorial. So whenever you see npr, it means the value of npr is n factorial by n minus r factorial. Right, so this is a permutation. If I take different order of the same objects, then that counts as a different permutation. So this is a permutation. How it differs from a combination is simply in that fact that the order of arrangement matters. So I had placed a lot of emphasis on the order of arrangement of the objects, right? But when I want to find the combinations, the order of arrangement does not matter. I only want to know in how many ways I can select r objects out of n. But if I have to find the permutations, I have to select those r objects out of n, and also I have to arrange them in some ways, which we'll see just now. So if we know the number of permutations, which we've calculated very naturally, npr equal to n factorial by n minus r factorial, highlighting it. Right, npr equal to n factorial by n minus r factorial. So if I want to find the combinations, that is a case where the order of arrangement of all these objects does not matter. Let's say this is equal to some number m. M equals number of combinations. Number of combinations for selecting r out of n objects, and distinct objects, obviously. So since the order of arrangement of the objects matters for permutations, and since the order of arrangement for a permutation matters and it does not matter for the combination, the only difference between these is that I must arrange those r objects in a certain amount of ways, right? So what you can think is, in order to gain the number of permutations, I must find the ways to select r out of n objects and then arrange those r distinct objects in r places, right? So you can now think that we have all of these numbers. Permutations equal to combinations into order of arrangement. And this simply comes from the multiplication principle. If I want to find the number of permutations, I must form a combination of all those objects, and then I must arrange them, and emphasis on and hence I multiply them by the order of arrangements. So the number of permutations, that's npr equal to m into order of arrangement of r objects in r places. No, it won't be n here because I've already selected r out of n objects through this task, through the number of combinations, and now I have to arrange those r objects in r places, which we've already seen before as per the last lecture, that is r factorial. So m equals npr by r factorial equal to n factorial by r factorial into n minus r factorial. And this is the second and most common result of permutations and combinations. We denote this number, the number of ways of selecting r out of n objects, or the number of combinations of r out of n objects, equal to ncr equal to n factorial by r factorial n minus r factorial. Okay, so these are the two primary or very important results of this chapter. Okay, so the theory of these two topics is pretty much this: the derivation of the number of permutations of r out of n distinct objects and the combinations for the same system. Now, because I've said n distinct objects, note that we will also have a different formula which we can derive in a similar fashion for n identical objects as well as groups of identical objects. We will be looking at that in the next lecture. In the meanwhile, let's look at some problems. So the first problem, I'll stick to permutations for a while. Find the value of 5p2 and 4p4. Okay, so this is 5 factorial by 5 minus 2, 3 factorial, so 120 by 6, 20, and 4 factorial by 4 minus 4 factorial, or 4 factorial by 0 factorial, 24. And this, if this is a rather useful result to know, that npn npn is just equal to n factorial. Here's a common example on how to permute. Say I have a bookshelf, and on this bookshelf there's books of 3 different topics: English, physics and maths. For English, say that there's 2 different books. For physics there's 3, and for maths there's 4. So these books are to be placed in a shelf so that all books on one subject are together. Rather, let's take different cases. One is, in how many total ways can I arrange these books? Now the arrangement of books here is it matters because it perhaps, since we're arranging it on the bookshelf, the arrangement matters. So we have so a total of 9 books, right? This is 9 books, and if we have to arrange 9 books in 9 places, the total number of ways to do that is 9 factorial, or 9p9. So that is equal to 5040 into 8 into 9. Or 362880. The value does not matter much, but just to know. So this is one case. If there is no constraint on the arrangement of the books, no restriction on the arrangement of books, then yes, this is the answer. But another case is, say I want to arrange these books such that all books of the same subject are together. All books of the same subject are together. So the two English books are together, three physics books are together, and four maths books stay together. So what you can do, second case, if PEM books sit together, in this case what you can do is you can consider each subject to be a group of objects. So E is one object, P is one object, M is one object, and now the arrangement and selection of these three objects matters. So n, the answer will be equal to 3 factorial, right? Because there's three sort of groups of distinct objects, and we can arrange them in 3p3. Since we've done permutations, I can arrange them in 3p3 ways. So the number of ways to arrange 3 out of 3p3 into, because our job is not done yet. Once we've arranged all of these books by subject, we also need to sort the books between themselves. So those two English books, the arrangement of those two books also matters. Since we have two English books and we have to arrange them in two places, 2p2. Since we have three physics books, to arrange them in three places, 3p3, and four maths books, so 4p4. So this is 3 factorial into 2 factorial into 3 factorial into 4 factorial. Okay. Next question. This is question 3 if I'm not wrong. So here's the next question. It's sort of a combination of several different questions. Again, so like the word space I had given you, let's take the word algorithm. So the task is to determine the number of arrangements of the letters of this word with a few constraints. One, vowels are together. If the vowels are together, so how many vowels exist in this word? A, O, I, 3 vowels, and the rest are L, G, R, T, H, M, 6 consonants. If the vowels are always to stay together, then like the previous example, I can group the vowels together as one case, as one group of objects, and I can have 6 individual consonants, which means I can consider this to be A, O, I and L, G, R, T, H, M. So this is 1, 2, 3, 4, 5, 6, 7. 7 objects which I must arrange in 7 places. Right? Agreed that the word in itself contains a total of 9 letters, but since we've grouped 3 of those letters together, we have reduced the total number of, you can say, distinct objects in this system, and hence we have 7 objects which we must arrange in 7 places. So n is equal to 7p7 into 3p3, because I also have to arrange A, O, I in their respective places. So this is 7 factorial into 3 factorial. You can compute the value for yourself. Another case is if consonants are together. Consonants are at even positions. So now we can look at it by drawing each, by making a space sort of diagram like this. There's 9 letters. Consonants must be at even positions, right? So how many? There's 6 consonants in total, and the number of even positions is this one. So the number of even positions is this: 2, 4, 6 and 8, which means that there are 4 even positions in which the consonants can be placed. So n is equal to 6, because we have 6 objects. If the consonants are at even positions, we have 6 different consonants: L, G, R, T, H, M. And there's 4 even positions in which 6 consonants have to be placed. So I have to select the 4 consonants out of 6, and then I also must arrange them, right? So 6 consonants must be arranged in 4 ways, 6p4. Now the remaining 2 consonants and the remaining 3 vowels, the arrangement of those letters does not matter. So 6p4, I've already placed 4 of the letters, which means I have 5 letters remaining, and that I can place in 5 factorial ways. So at this position, 1, 3, 5, 7, 9, I have all the other I have the other 2 consonants and the vowels left, and I can place them in any way I need. There is no constraint on that. So simply 6p4 into 5 factorial. Another case is O is the first letter, T is the last. O is the first letter, T is the last. What can I do here? The easiest solution to this is just place 0 and T in the position that is required. O and T placed. Now A, L, G, O, R, I, T, H, M. I've used up O and I've used up T. I've used up 2 out of 9 letters. So I have 7 letters remaining. Okay. And I have to place them in 7 ways. 1, 2, 3, 4, 5, 6, 7. 7 ways. So the number of ways I can do that is 7p7. Answer is 7p7 equal to 7 factorial. And the last case is if no 2 vowels exist together. If no 2 vowels are together. Last case is no 2 vowels are together. If no 2 vowels are to be together, then you can imagine that after every vowel there's a consonant, right? So if there's, in the given word algorithm, there's 6 consonants: C1, C2, C3, 4, 5, 6. You can imagine that between these consonants there are gaps between and before or after. So these are the gaps. The blanks that I've written, these are the gaps. These gaps may or may not be filled with a vowel, but it does not matter now in which order I place the vowels, because the condition that no two vowels are together will always be satisfied, because there will be at least one consonant in between two vowels, right? It can be this way, or it can be so it could have been that, or it could be this, right? So you get the idea. So if I have 6 consonants, C5 and C6, if I have 6 consonants, you can observe that these 6 consonants create 1, 2, 3, 4, 5, 6, 7 gaps. 7 gaps are created by 6 consonants, and 3 objects must be placed in these 7 gaps. Okay? 3 objects must be placed in these 7 gaps, and their arrangement also matters. So, I have the 6 consonants can be arranged in 6 factorial ways, or 6p6. I'll write in terms of 6p6. This can be arranged in 6p6 ways, the consonants, and I have to place 3 vowels in 7 places. That can be done in 7p3 ways. So the answer is 6p6 into 7p3. And let's look at a final problem for permutations. Question 4. Let me write it here. Yeah. In how many ways can 5 books, distinct obviously, be arranged on a shelf subject to the following conditions? One is no restrictions. No restrictions, we know it's 5p5, 5 factorial. 2 books are always together. 2 specific books are always together. 2 books are always together. Two books are always together. So what we can do is, out of these 5 books, we place these 2 books together. Say the books are B1, B2. We place these 2 books together. So we take B1, B2 as one group of one cluster of objects, 2 distinct objects, and we treat that as a distinct objects of its own. So we have 1, 2, 3, 4, and this we can arrange in 4 factorial ways, or 4p4 ways, and then I must also arrange b1 and b2 amongst themselves. That I can do in 2p2 ways. And 2 books are never together. Now, looking at the previous 2 examples, previous 2 questions, you can perhaps try to find this answer, right? So the total number without any restriction of if those 2 books are together or not is 5 factorial, and if those 2 books are always together, it is 4 factorial into 2 factorial, right? So and so our case now is if these 2 books are never together, and what we can see is these 2 events of the 2 books being together and not being together, these are sort of mutually exclusive. That means either the book will all be together, either those 2 books will be together, or they will not be together. In other words, we can add up the number of ways, we can add up the answer to this problem, say it's n, and the number of ways to arrange such that two books are always together, and that will give us the total number of ways. So our answer will be 5 factorial minus 4 factorial 2 factorial, or this is 4 factorial into 3 factorial. Okay, so let's look at one final question. One final question. 3 boys and 3 girls are to sit in a row. So basically find the number of ways we can arrange them to sit together. If there's no restrictions, no constraints, you know the answer already, 6p6, because a total of 6 people, 6 factorial. If there is a girl at each end, so there's 6 places, right? And I place a girl at each end, so I place a girl at each end. Now the number of ways I can select these two girls who will be at the end is 3p2, right? The number of ways I can select and arrange those two girls at the end. So if the girl is say A and B, if out of A, B, C I choose A and B, then it can be A and then B, or B and then A, right? So the arrangement also matters. So out of 3 I can select them in 2, select and arrange in 3p2 ways. And because I have 4 people now left, 1 girl and 3 boys, I can arrange them in 4 factorial ways, or 4p4 ways, sorry, 4p4 ways. There's a girl at each end. And the final case, the boys and girls sit alternately. So 6 places. Okay. 6 places. Either I can do it this way, right? Or I can do it this way. G, B, G is girl, B is boy. So boy, girl, boy, girl, boy, girl, or girl, boy, girl, boy, girl, boy. There are these 2 different cases and we'll have to add them up. This can be done in 3 factorial times 3 factorial, or 3p3 times 3p3. I'm not doing 6p6 here because there's a constraint on exactly where the girls and boys are sitting. So because the places are fixed, I just now have to arrange them in those 3 places. So 3p3 times for the girls and the boys, 3p3 and 3p3, and the same goes for this case. So 3p3 into 3p3, and the total will be twice, or just the addition of these 3. So 2 into 3 factorial into 3 factorial, right? So this is today's lecture. Thank you for watching.